everyone. Thank you for the kind introduction. Today I'm going to present our paper because every sensor is unique and so is every pair, handling dynamicity in traffic forecasting. This is me. My name is Aryan Prabowo, and those are my supervisor, Dr. Wei Xiao, Dr. Peter Konyush, and Professor Flora Salim. And Dr. Hao Shui is the postdoc in my group. Right now I'm a postdoc in USW. Cyril is the one who funded my PhD. And I'm still a student in my final months in RMIT University in Melbourne, Australia. It's a long flight. It's a long flight. So let's start with traffic forecasting. So let's start with the sensor. The sensor that we use in traffic forecasting is called inductive loop traffic detector, and the idea is we put some wire loops on the ground in the asphalt, and the idea is if we put alternating current in one of the loop, it will induce a current in the other loops, and depending on whether or not there are metals around and how fast the metals are moving, it will induce a different kind of current in the other loop. And if we were to measure that current, what we have is we will have basically a metal detector, and not only that, we can measure how fast the speed of the metals moving. And this is how we get a traffic detector. We can detect bikes, we can detect cars, we can detect vehicles. From the data perspective, this means that every single loop detector is now generating a time series. In this case, we are aggregating speed for every 5 minutes, and this is what traffic forecasting is. The idea is where we get an hour of traffic, an hour of past traffic, about 12 time steps, and we use that to forecast what the traffic will be in the next hour, in the next 12 time steps. Not only, but if we put these sensors, not only we have one sensor, but we have hundreds, thousands, or even like 10,000s the size of an entire state, 10,000s of these sensors all over the entire highway network. We will have a sensor. We will have a sensor networks like this. And this data is about 300 sensors from the Bay Area in California. And every single dot point is a sensor like in the picture, and every single dot point will generate a time series. And so this is what our traffic forecasting task is. It's about multivariate time series forecasting. The idea is we forecast the future. We use the recent past from all the sensors together at the same time in order to forecast what is the future traffic like at every single sensor. And so that is, in brief, what is traffic forecasting task that we have in hand. So let's start with our first point in the title, how every sensor is unique. One way to analyze a sensor is by using a fundamental diagram. And that is we are simply plotting the average density. We can just simply count how many cars in 5 minutes, and the average velocity, right? What is the average speed in the same 5 minutes, and we will get a fundamental diagram like this, at least in theory. So if we only have one car, that car is going at a speed limit, right? Everyone is a rule-obedient citizen, rule-obeying citizen. If we have two cars, everyone is still flowing at the speed limit. And this keeps on happening until we reach a critical point. And from that point onwards, whenever we add another car, everyone will start slowing down. And this will continue until we reach congestion state. And at least this is the theory, this is the classical model of how traffic works. What if we check what the data looks like, right? This is from one of the sensor, and we just plot the fundamental diagram. We can see that the shape looks very different, right? There are still some similarities. There's still some downward slope as expected, right? But there's no clear congestion state. There's no clear critical state, right? it's also a very wide distribution, right? It's not a very thin straight line, but at every density there's a wide distribution of possible velocities. And but maybe we just pick the wrong sensor, right? This is just one sensor after all. Maybe this is an animal sensor. Every other sensor follows the ideal fundamental diagram. And so, but unfortunately, it is not. Every single sensor apparently has a very unique and very different shape and distributions, as we can see here. So that is the first part of our observation, that every sensor is unique. And so we're moving on to the second part, and so is every pair. So these are association plots, and the idea is simply for every single plot, in the x-axis is the flow at sensor A. Flow is just a count, similar to density, how many cars in the past 5 minutes. And the y-axis is also flow, but at a different sensor, sensor A and sensor B. And sensor A and B are like random location, right? So these are 8 different pairs. So what does it show is that, for example, we can see that the sensor on the bottom left is very strongly correlated, right? When one sensor is slow, the other one is slow. When one sensor is fast, when one sensor has a very low count, the other one also has a very low count. When the other sensor has a very high count, the other one also has a very high count, right? However, we can see some sensors are much weakly correlated, right? So every pair is also unique, and not only that, for every single pair, it also changes over time. So, for example, the one in blue is in weekdays, and the one in red is in weekend. So, not only every single sensor is different, but even the same sensor is also different at different time. So this is where both the spatial element and the temporal elements comes in, and I think this figure is clearer. So all the blue ones, or the weakest one, looks like a triangle, except for the second Monday, maybe it's a long weekend. Whereas all the weekend ones have a very stronger correlation, right? It looks like a line instead of like a triangle. And so that is our second point, right? We established that every sensor is unique, and every pair is also unique. So the question is, how are we going to handle this for traffic forecasting? And so we propose a new architecture called G-SWaN, that stands for Graph Self-Attention Wavenet. And this is the general architecture. We're using the graph wavenet as a backbone. It's an established part of the literature. But the part that is new is the red square, and that is the spatial graph transformer. That is our contribution. But before that, let us go through have a quick overview of the architecture. Yeah, good. So this is our input, multivariate time series, and we have two encoders. One is to encode the speed or the density, and the other one is to encode the time of day. A feature that has been established in the literature, that it is a useful feature. And then we have multiple, and then we put this into multiple layers of this temporal block and spatial block. So this blue block is the temporal block. Some people call it wavenet. It's also known as TCN, temporal gated network. And then this is SGT, our spatial graph transformer, our contribution. And after several layers of this, we give to the final decoder. It's basically just MLP, fully connected layer, and before we make the prediction, and we use MAE's loss function. What this part, this spatial graph transformer, is a GNN. It's a graph neural network. It needs the spatial information of the network, right, which we didn't have before. So it gets the spatial information from here. This is the road network connectivity. Not only not only we know the sensors, but we also know the distance between the sensors, and we use a radial basis function to construct the first adjacency matrix based on the physical road connectivity. But it is actually not good enough because the geometry in the data might be different than the actual physical geometry. So in order to solve that, in order to discover the hidden geometry that we need in the data that is not in the physical road network, we use this adaptive adjacency matrix, and this is done by getting two randomly initialized matrix. And what we do is we do a matrix multiplication, and to generate this adaptive matrix, and we simply concatenate them. So we have multiple adjacency matrix, and we use this adjacency matrix to fit into the GNN in order to give them the spatial information of how the nodes are connected to each other. And so this is our SGT layer, our spatial graph transformer. What it does is it has a very similar architecture with a transformer. It uses these node embeddings, E1 and E2, and these node embeddings are the one that captures the unique behavior for every single node. And so we put them into a key and a query layer as usual. And when we get this attention matrix, what we do is because not everything is because there is some bias with the spatial relationship between the nodes. We use this attention to mask over the adjacency matrix before we use this as a final attention, and then we fit this final attention to the typical GCNY. This way, what does it mean is that by engineering it this way, our every single layer is now adaptive to every single node, so that it doesn't behave the same way for every node, but it can behave uniquely for every node. And not only that, because of this keys and query pairing, it can also react adaptively with every single pair. And most importantly, finally, this node embedding is combined additively with the output from the previous layer. What this means is that this will help us detect if there are the temporal changes, if the temporal changes such as the weekdays and the weekend for every single node. And this is our main contribution. We evaluate this on four data sets. These are all open data set, and these are all famous data sets in this task. Unfortunately, they are from California, and these are quick statistics about the data sets. Few hundred sensors, few hundred to few thousand edges, and it's typically a few months. We have some with speed, and we have some that measures the speed, some that measure the flow, and they are distributed as such. And these are the results. These are the results. We are always either the best or the second best. This is our contribution. G-SWaN at the very bottom. This is for the speed datasets, Metro LA and Dynamicity. And this is the result for the other two datasets, for the other two flow datasets, and where we are consistently at the state of the art. And we also did an ablation study. I just present our main contribution. We also have some small contribution, and the idea is we also analyze what kind of augmentation might be useful for traffic. And then what all of this shows is that the most important component is not the difference. the I forgot the name, all the different perturbations on the data, but it's our SGT, right? Because this is the performance of the full model, and if we remove this SGT, it has the most drop in performance. Yeah, and so we also inspect so we have the setup, and then we want to inspect what are our node embeddings learning, right? Are they learning something useful or not? And so what we figure out is in our whole setup over here, there is no information about the coordinates of the nodes of the sensors. What we have is we only give the connectivity information, so not the location information. And what we do is we use a linear probe, very similar with what people do these days with GPT type architecture in NLP or in Fusion. We use a linear probe, and it shows that we can actually recover the coordinates from the node embeddings alone, even though so somehow there is some sort of node embedding information learned by the architecture. And this is the last slide. So we have two adjacency matrices, right? One is derived from the physical connectivity, which is shown the one in black. But we also have the learn adjacency, which is the one shown in red on the right, and this is where all the one with a very high weight, and it shows that the physical connectivity is understandably connecting all of the nodes that are close together. That's the idea of physical connectivity, right? However, it shows that over here it shows that there are some nodes that are very, very far away, but the architecture thinks that it is required to connect them together very, very strongly. So they are very, very helpful. So this connection is very helpful in forecasting future traffic. So these are our discovery. So thank you very much. This is the QR code to our code. And yeah, thank you. If you have any question.
Any question, anyone?
Yeah, thank you. So in the end, you talked about the actual physical and the adaptive connectivity. Is that also the hidden embedding you showed earlier, or was that something else?
So yes, we use the node embedding for two things. One is to generate the adaptive adjacency, the adaptive connectivity, the one at the last slide.
Yeah,
and we also use it for this as well. So we use it yeah.
Okay, and so if I might follow up with another question to that. So the idea is that you learn better connections than the physical ones, right? So what's like the motivation? Shouldn't the physical one already give you all the dependencies that you might encounter?
No, I think I learned this. So the idea of using this adaptive connectivity is not ours. It's already been done before, but no one actually looked into this and what it's actually doing. We are the first that does it, and this is also. And I think this is also the case with other domains that is not traffic. I think it's shown that whatever's the input connectivity that we actually get from the data might not be the best connectivity that we need to solve some graph task. I learned this from reading Michael Bernstein. I think he was in machine learning. He was the head of machine learning group at Twitter. I'm not sure if he still is. But yeah, I think he does a lot of work in graph neural network, and the idea is the graph is just an expression of the underlying geometry in the data, and then the geometry in the data and the geometry in the data that we're learning might be different.
Thank you.
No worries.
Hello, thank you for the talk. I was wondering, like, what are the actual applications for like a traffic engineer or someone who's in civil engineering if they know the physical connectivities of these roads?
I'm not sure. Good question. I think this is there. So I haven't looked into that yet, but there are some ideas that I know from other people in my group, and the idea that deals with spatial temporal data, and the idea is that it might be the case that these places might have the same behavior because they are near the same point of interest. For example, both of them, maybe the one at the top left and the bottom right, maybe both of them are near the similar schools, or they are both similar types of neighborhood. Yeah. So we have to confirm that with actual data, but those are my suspicions. Thank you.
I think due to the interest of time, let's take a further question offline. And I think Aaron will be around to answer further questions.
Thank you.
Thank you very much.